Hey, welcome back. Today we will talk about combinations with restrictions. So far we have talked about trying to enumerate the number of combinations of various kinds. This one is slightly different in that it imposes a certain restriction on the allowed combinations. So here is a prototypical problem. It says find the number of strings of length n consisting of zeros and ones in which you do not have two successive ones. Okay, so let us try and write down a few such examples. Now what are such strings? So let us say, okay, what is n here? N of course is the length of the string, so the length of the string could be 1, 2, 3 and so on. So let us do the following. Let us write down a table. And so on, and for each value of n let us first enumerate the strings which are allowed, in the sense they satisfy the required restriction. So if I only have a string of length 1 consisting of a 0 or a 1, well, there are two possibilities. I can just take the string which just has a 0, or I can take the string which just has a 1. So both of these are allowed strings because you do not have two successive ones appearing. Okay, so let us do the case n equals 2. So I have a string of length 2, so I could have 0 0, or I could have 0 1, or I could have 1 0. Now the fourth possibility, which is 1 1, is no longer allowed in this case because you have two successive ones. Okay, now let us do maybe one more. 3, string of length 3, you can have all three zeros. You can have 0 0 1. Let us see, I can have 0 1 0. Now maybe I will write all of them down and we will get rid of the ones that do not satisfy the constraint. So 0 1 1, and then I have 1 0 0, 1 0 1, 1 1 1. So I also have 1 1 0, and then I have 1 1 1. So let us see, we got 6 plus 2 8, that is the total number, out of which we need to disallow 0 1 1, 1 1 0 and 1 1 1. Okay, they are not they contain two successive ones. And so let us also do the following. Let us count the total number of strings. Okay, so let us say the number of such strings, of allowed strings. So let us call this number something. Let us call this f of n. So remember, the number of allowed strings depends on n, of course. So let us call this number f of n. So here it is 2, f of 2 is 3, there are 3 allowed strings, f of 3 is 1 2 3 4 5 and so on. Okay, so far we have figured out what happens in the initial cases. Now to really understand what is going on, let us try and do the case n equals 4. So as you can see, enumerating these strings gets harder and harder, but let us sort of see the pattern that that can be obtained from this. So if you take n equals 4, what you are looking for is a string of length 4. So maybe we will do it here. So I need a string of length 4 with zeros and ones. So of course the very first entry in the string is either a 0 or a 1. So there is a bunch of strings which start with a 0, and then here is the other possibility. So let me write down case 1 and case 2, things which start with a 0 and strings which start with a 1. Now suppose the string starts with a 0, what does it tell you about the remaining 3 places? So what do you do with the remaining 3 slots? Well, observe that the condition says you cannot have two successive ones, but well, the first entry being a 0, that says that the next entry can be pretty much anything you want, right? It could be a 0 or a 1, for instance, and then you have another entry and another entry. So observe that these 3 entries have the following property, that this must be an allowed string, meaning it should not contain, so this must be an allowed string of, well, of one smaller length, of length 3. Okay, so this is case 1. If your string starts with a 0, then what follows it must be an allowed string of length 3, okay, without two successive ones. Now case 2 is the following. if the string starts with a 1, then what can one say about what follows it? Let us look at the constraint. It says that you cannot have 2 successive 1s in your string. So since the first entry is a 1, this had better be a 0. Okay, so the first 2 entries get determined, and now observe that what follows. So now that I have a 0, the next entry can be a 0 or a 1. So what we have in these 2 slots had better be an allowed string of length 2. Okay. So this tells you how to go about enumerating all these strings. What you would do is the following. In order to write down all strings of length 4, you start with the allowed strings of length 3. So let's get rid of the ones that are not allowed. So here are the 5 allowed strings of length 3, and to each of them you will adjoin a 0 in front. Okay, so let's take all these guys and prefix each of them with a 0. So I have 0 0 0 0 0 1 0 1 0. So I'll first write the ones of length 3 and prefix each of them with a 0. Okay, so these are 5 strings of length 4 which begin with a 0, and in addition you also have the ones which begin with a 1, and in fact those must begin with a 1 0 as we just saw. So what you now do for these guys in case 2, you go one level lower, you look at the allowed strings of length 2 and you prefix each of them with a 1 0. Okay, so I had these 5, then let me write strings of length 2 0 0 0 1 1 0, and I prefix each of them with a 1 0. Okay, so what you get are essentially these 2 cases, and that makes for easy enumeration. So what's the total number here? Well, observe it's the number of allowed strings in the one preceding level plus the number of guys in 2 steps before it. So this number is actually 8, and how did we obtain this? Well, it's the one preceding number plus the number which came 2 steps before it. Okay, so this analysis in fact tells us the following. Observe what have we just shown. We have realized the following, that f of n is just the sum of the 2 preceding numbers. Okay, and well, of course this only makes sense if n is at least let's see, n is at least a 3. So in order to compute f of 3, f of 4 and so on, all you need to do is just take the sum of the 2 preceding guys. Okay, and in addition what else do we have? We also know the first 2 values of f. For instance, f of 1 we know is a 2, and f of 2 we know is a 3. Okay, so these 2 are often called the initial conditions, the initial values if you wish. These are the initial values, and this relation here, well, it's appeared several times before in our lectures. So we have had occasion to encounter these guys when we talked about, for instance, the Chebyshev polynomials, where of course all these guys are actually polynomials in a variable x. Here they are numbers. These also appeared when we were doing the problem of counting monomials in polynomials of many variables, counting monomials of a given degree. Those were again given by a recurrence relation. So this equation here is what's usually called a recurrence relation, which determines a certain term of the sequence in terms of the preceding terms. Okay, now here's the problem that we would really like to understand. How do we find a formula for f of n? So find a formula for f of n. Okay, it's easy to write down the initial values, right? You just keep adding. It's whatever 2 3 5 8 8 plus 5 13 21 34 and so on, but what we want is, given n, a formula which tells you what f of n is. Okay, so here's a slightly more general problem which basically concerns recurrence relations. If you are given arbitrary recurrence relations with say even coefficients in front, one can still use a similar approach to solve it. So let me pose a more general problem. So here's a more general problem. So given a recurrence relation, so given a sequence of numbers f of n greater than or equal to 1, which satisfies, suppose a sequence f of n satisfies a recurrence relation, f of n is given by some a times f of n minus 1 plus b times f of n minus 2. So this is for n at least 3. And what are a and b? A and b can be arbitrary real numbers or complex numbers and so on, some constants, and with some initial conditions. So and of course I need to tell you what f of 1 and f of 2 are. Okay, so f of 1 is given to be some number p, f of 2 is given to be some number q. Okay, and the problem now is to find a formula for f of n. So find a formula for f. Okay, so let's try and do this. So the key observation is the following. Well, one of the key observations, so here's a key fact concerning sequences given by recurrences. If suppose you have another sequence f of n, okay, so I'm calling it capital F, or maybe I'll call it g of n. So suppose I have another sequence g of n which satisfies the same recurrence and the same initial conditions, satisfies the same recurrence as f and has the same initial values as f, then g and f are in fact equal. Okay, so what it says is the recurrence relation together with the initial conditions uniquely determines the sequence f, and it's sort of easy to see why, because the first two values are the same for both g and f, and how you form the successive values is also the same. It's given by the same prescription. So for instance, in this example that we just talked about, if g of n is the sum of the two preceding values and the first two values are 1 and 2, or let's say 2 and 3, then there is only one way in which you can determine the values of g, right. So you have 2 and 3 are the starting values, so the next value must be a 5, the next value must be an 8, the next value must be a 13, and so on. So it's forced, there is pretty much no choice at all here. Okay, so this is one elementary but very useful observation. And so here's another somewhat more surprising observation, so not so obvious at first. So here is an approach to solving this recurrence. Consider, so here's the very interesting ingredient here, consider the quadratic equation. Okay, so observe we assume that f satisfies the recurrence f of n equals a times f of n minus 1 plus b times f of n minus 2. Okay, now here's the following thing that we do. We take those same numbers a and b and then form a quadratic equation, write x square equals ax plus b. So observe, this is just another way of saying x squared minus ax minus b is 0. Okay, so maybe we could do that. Let's write this as x squared minus ax minus b equals 0, and let's pick a root of this equation. So a quadratic equation has two roots. Of course the roots could be complex numbers, but never mind. So let r be a root of this equation, let r be a root. So you pick one of the two roots, then and consider define a sequence g of n as follows. Just take powers of r, just call it r power n for all n at least 1. Okay, so what we have done so far is to take a root of the quadratic equation and you form a sequence. Now of course the sequence is a sequence in general of complex numbers, but never mind. So you have a sequence. The claim is that in fact G satisfies the recurrence of f. So G of n is exactly A times Gn minus 1 plus B times Gn minus 2. N greater than or equal to 3. So here's a surprising fact that the sequence G of n that we have constructed actually satisfies the recurrence that we began with, okay, and the proof is more or less straightforward. So observe this equation, so we just need to show that this equation holds. So this equation is just the following equation, that this is r power n, this guy is r to the n minus 1, that's r to the n minus 2, and of course this this is all we need to check, is this true, and just observe that if you cancel off an r to the n minus 2 from both sides, this equation just is the same as r squared equals ar plus b. How do you get this? By cancelling of a common factor of r to the n minus 2 from both sides of the equation, and of course that was the beginning assumption on r, that it is a root of that equation, okay. So of course the proof is very simple. Once we know what we want to prove, it's rather trivial to see that it's true. Okay, so this is somewhat surprising that you can actually manufacture a sequence which satisfies the given recurrence by just taking a root of this quadratic equation and just raising it to various powers. Now of course so if suppose G satisfied the initial conditions, if it had the same initial values as f, then we would be done, because then this would just be G has to equal f according to what we just said. So this would pretty much give us a formula for f of n, okay. So of course it's too much to expect that the initial values of G equal the given initial values of f. So observe what are the initial values of G in this case. So if I put n equals 1, this is just r power 1, and if I put n equals 2, this is going to give me r square, okay. And as I said, r and r square are in general some complex numbers, r is the root of this equation, and of course these may not be the given initial conditions. So for instance f of 1 and f of 2 were given to be p and q, these may fail to equal that, okay. But this is a very good beginning. We already have at least a way of ensuring that the recurrence is satisfied. It's only the initial conditions that require some work. So here's a further case. Now suppose, let's assume the following. Suppose this quadratic equation has two distinct roots. Suppose that the quadratic equation that we wrote out has two distinct roots, let's call them r1 and r2, then observe we have two different solutions. So let's call it G1 of n is r1 power n, here's a sequence that satisfies the recurrence, G2 of n equals r2 of n. So both these sequences, they satisfy at least the recurrence relation. And so here's another key fact which tells you how to manufacture many more sequences which satisfy the recurrence, starting with two such sequences, okay. If you know two sequences which satisfy the recurrence, the key fact is the following: if you form any linear combination of these guys, so you define G of n, let G of n be some constant C1 times the first sequence plus another constant times the second sequence, okay. This is what we have called once before a linear combination of these two sequences. Any linear combination will also satisfy the recurrence, that is the key thing, okay. So let G of n be defined like this, with what are C1 and C2, they can in fact be any complex numbers. Then G of n also satisfies the recurrence. Okay, so now what this gives us is a way of manufacturing tons and tons of sequences which satisfy the given recurrence, because we know r1 and r2 are distinct, so here are two distinct solutions, and here is a prescription which allows you to construct many more solutions starting with two solutions. Now that already gives us some hope that maybe one of these guys will in fact have the required initial values. Okay. So if we can somehow arrange these constants C1 and C2 such that g of n has the required initial values, then we would have found a formula for the required sequence f of n. So now the problem really reduces to the following. What we would like to do, we want to find constants such that g of 1 exactly gives you the required initial condition P and g of 2 gives you the required initial condition Q. If we can do this, then f and g would automatically be equal. So observe, if we can do this, then this would imply that the sequence f that we want must in fact equal the sequence g. Okay, and that would give you a formula for f of n, because g of n is of course just given by a formula. It's given by c1 r1 power n plus c2 r2 power n. Okay, so let's just see this in the example that we want. So the case of the sequence f of n that we started out with. So observe here where f of n was f of n minus 1 plus f of n minus 2. This is the same f that we started out with, the number of 0 1 sequences of length n which do not contain 2 successive ones. So this is for n at least 3, and we had the following initial conditions: f of 1 is 2, f of 2 is 3. Okay, so here's our procedure. We start with a quadratic equation. So sometimes it's called the auxiliary equation. So it's the following quadratic equation here. It's x square equals x plus 1. We solve this equation. So how do we solve this? Well, we use the usual quadratic formula. So here's the quadratic equation, and here there are two roots. So let's write those two roots down. R1 equals 1 plus root 5 by 2, and R2 is 1 minus square root of 5 by 2. Okay, so there are two distinct roots in this case, and so what does our prescription say? It says you look for solutions of the form. So let's form the sequence g of n. So let's define g to be a linear combination c1 r1 power n plus c2 r2 power n. So you define g in this way. This guy certainly satisfies the recurrence relation, and all we want is for it to satisfy the initial condition. So now let's impose our conditions. So let's impose the following conditions. G of 1 we would like it to be 2, and g of 2 we would like it to be 3. So these are the two conditions that we would like to be satisfied. So what do these amount to? G of 1 is just c1 r1 plus c2 r2. G of 2 is c1 r1 squared plus c2 r2 squared. So what you now have are two equations for the two unknowns c1 and c2. Okay, so all we have to do is just solve these equations. So solve for the constants c1 and c2. Okay, so I'll just give you the solution here. So exercise check that here are the choices that give you the required initial conditions. So c1 in this case is 3 plus root 5 by 2 times the square root of 5, and c2 is 3 minus square root of 5 by minus 2 times square root 5. Okay, so here are the constants which you can just get by solving these two linear equations for the constants c1 and c2. So what does that give you finally? Well, it gives you a solution to the original problem. It says that the number of 0 1 sequences which have no 2 successive ones is in fact given by the formula c1 times. So what does this imply? Finally, here's our conclusion: the number of 0 1 sequences with no 2 successive ones must in fact be the same as g of n, because it has the same initial conditions and the same recurrence. So this is just, if you wish, 3 plus root 5 by 2 root 5. That's a constant c1 times r1 power n. R1 is this, plus the constant C2. So the constant C2 in this case is 3 minus root 5 with a minus 2 root 5 the bottom times 1 minus root 5 by 2 power n. So here is a formula for the function f of n that we wanted, and it is rather surprising that that this will always work out to be a positive integer, right, as it should, because f of n after all counts the certain number of configurations of a kind, and it is rather strange that with all these square root 5's floating around here, that at the end of the day this always works out to be a positive integer. Okay. So check for certain values of n, just plug in various values of n to see that this in fact gives us at least the first few terms correctly. Okay, so next time we will talk a little bit more about these very same sequences and maybe where else they appear in a few other problems. So we will talk a little bit more about that next time.